So Doug, why do we use sounding rockets to study the auroras?
The sounding rockets have many advantages. They're sort of complementary to the satellites. So the satellites usually have a very extensive instrumentation, they're very expensive, very complex, and they have a lot of capability. And what they do is they fly more or less horizontally through the region. So one advantage of sounding rocket is it's suborbital, means it doesn't orbit. So it goes up and it comes down. So if you want to get a vertical profile of what's happening in a region, you might use a sounding rocket because you can say, I'm going to launch from here, I'm going to go up, and I'm going to come back down. I'm going to measure as a function of height what's going on.
Right.
The satellite gives you a complementary view. What's happening as a function of horizontal.
Just give me a slice.
A slice,
right.
Exactly.
Now, do you ever launch a sounding rocket and have a satellite going over the region at the same time?
People do that. Tom Woods at the University of Colorado does that with the SDO. They've got an instrument on board SDO that needs calibration. So they're looking at the sun, they're making the same measurement with the sounding rocket to try to get a good calibration. There have been other attempts to have a satellite go by, and maybe not exactly at the same moment, but nearby in time to do an underflight. And we want to do more of those experiments.
Now, you just had a successful mission just recently called VISIONS. So what's the VISIONS project all about?
Well, VISIONS, we like to have these acronyms. So VISIONS is sort of an acronym that tells you what the mission is. It's using imaging as opposed to direct measurements along the trajectory to measure a phenomenon that we've known about for a long time but never have had pictures of. And that phenomena is called the auroral wind.
The auroral wind.
The auroral wind.
Wow.
You've heard of the solar wind.
Solar wind, yeah.
Yeah. The auroral wind is a wind of gas or ions that come out of our atmosphere, and they're driven out by the aurora. The aurora comes in, heats the atmosphere, gets it energized, and boils this atmosphere off. So it's a pretty weak, thin stream of gas, but it turns out to be very important because space around Earth is so empty, the magnetosphere is so empty, that having this gas, this oxygen flow out, can dominate, at least temporarily, what's happening out in the magnetosphere. And what drives it out is the magnetosphere itself. So it's a feedback loop where the magnetosphere drives the aurora kicks the oxygen and the auroral wind out, and that regulates or feeds back on the magnetosphere itself.
Now, is it a certain level of storm or before you launch that sounding rocket?
We launched into a pretty, I guess you might call it a minor substorm.
Okay.
One of the advantages of the rocket program, in addition to this vertical profile, is you can wait. And you can sit there and wait for 10 nights in a row and wait for hours each night to try to get the perfect time. With a satellite, if you zip through and then something happens, you miss it. You know? So we can wait until there's an aurora right in our path and right at the right time, and then go.
So what kind of instrumentation do you have on board to be able to make those measurements?
Okay, we have some things that would be familiar to you. We have a 4-channel camera where we have 4 different colors of light that we're looking down. We're taking pictures from above, looking down on the aurora, so we can see where the aurora is intense and where it might be driving this oxygen wind out. Our other major instrument is something called the MELINA instrument. MELINA stands for Miniaturized Low Energy Neutral Atom Imager. And MELINA, what it does is it makes pictures by looking at where atoms are coming from. So instead of looking at light to make a picture, it counts how many oxygen atoms are coming at every point. It spins around, it's like a catcher's mitt, and it looks over there and says, I've got so many oxygen atoms. It looks over here and says, I've got so many oxygen atoms. And it makes a map as it spins around, builds up where those pictures are coming from. We want to check how are they increasing as we go up in altitude? How are they corresponding to bright points in the aurora? So we have this camera looking down and saying, there's bright aurora over there. Is there also oxygen coming from that region? We also know that not all aurora are created equally. Some are very energetic and penetrate very low in the atmosphere, and those are usually green.
Right.
And then we have some that are less energetic, and they penetrate to a higher altitude, and they're red. And we have some evidence that the red aurora is a little bit better at energizing this atmosphere out. So we use our green and our red channel from the camera to say, okay, where are those oxygen atoms likely to be coming from? And we want to check our theory by looking where they're actually coming from.
And of course, when you're launching these sounding rockets, you're just not launching them anywhere in the country. You're trying to get into the auroral zone up by the Arctic Circle.
That's right. Yeah. Fairbanks is a famous place to study the aurora. I mean, we have all kinds of tourists from all over the world, mostly from Japan, actually go there because that's a very good place where the skies are clear, it's cold but not too windy, and the aurora is very common every other night, every third night. So it's a great place to look at the aurora. It's also the only land-based rocket range in the U.S. It's operated by the University of Alaska for NASA, and it's got this great downrange facility where you can put cameras and magnetometers on an ocean range like Wallops. You can't really instrument under where the rocket's flying because it's the ocean. But up there you can put your instruments under the rocket trajectory and really get a good picture from cameras looking up as well.
I guess it would be hard to launch from Wallops because we're so far south.
That's right.
Okay.
Yeah, we do lots of great launches from Wallops. We do have interests in the atmospheric physics over Wallops. There's a lot of interesting stuff that happens here. But to study the aurora, you go to, basically Alaska or Norway or Sweden.
Right. Now, you had a successful launch, so can you share some of the data that you received?
Sure. So we saw that we had great electrons coming down. We saw the aurora was very strong. and we saw that our auroral camera was working well. And the Molina instrument is a new instrument, so we're still kind of learning how it works, but we've already seen the fact that the altitude dependence of the oxygen atoms is very distinct. As we're below a certain altitude, the oxygen atoms don't travel very far, and they sort of run into each other. And then as we go above a certain height, they can start to travel long distances. We can start to make these pictures.
Okay.
We've already seen sort of a directionality to that, where we can say there are hot spots in these oxygen atoms. We haven't yet made the mapping of how those hot spots map to the auroral features, but that'll be our next step.